How do you debug variational autoencoder training instability? Imagine trying to teach a robot to draw perfect pictures, but every time it learns, its drawings become messy or it stops learning altogether. That's what training a variational autoencoder can feel like when things go wrong. Variational autoencoders are powerful tools in generative AI, helping us create new images, sounds, or even text by learning how to encode data into a smaller, manageable form and then reconstruct it. But getting them to train smoothly isn't always easy. Sometimes the training process becomes unstable, with losses exploding, the model ignoring the latent space, or even producing NaN values. So, how do we fix these issues? First, understanding the core of what a variational autoencoder tries to do is key. It optimizes something called the evidence lower bound, which balances two parts: the reconstruction loss, making sure the output looks like the input, and the Kullback-Leibler divergence, which makes sure the encoded data follows a normal distribution. If these two parts aren't balanced, training can become unstable. For example, if the cull term is too strong early on, the model might ignore the latent space altogether, a problem called posterior collapse. Next, check for numerical issues. NaN values often pop up when gradients become too large or when variance parameters are not properly constrained. High learning rates are a common culprit, causing big jumps in the model's parameters that lead to divergence. To fix this, lower the learning rate and monitor your training for NaN or sudden jumps in loss values. Using debugging tools that detect NaN during backpropagation can be a big help. Parameterizing the variance in a stable way is another important step. Instead of naively letting the model output any value for variance, use transformations like exponentials or bounded functions to keep variance positive and within a reasonable range. This prevents the model from producing invalid probabilities or exploding gradients. Balancing the cull divergence term is also vital. If the model relies too heavily on it early, it might ignore the data, leading to poor reconstructions. A common trick is to gradually increase the weight of the cull term during training, a method called cull warm-up. This allows the model to first learn to reconstruct well before regularizing the latent space. Regularization techniques like dropout or batch normalization can help improve training stability by preventing the model from overfitting or collapsing into a few modes. More advanced methods, such as importance-weighted autoencoders, give better gradient estimates and help the model explore the latent space more effectively. Monitoring the latent space during training is a good habit. Visualize the distribution of the encoded data to see if it matches the prior distribution, usually a standard normal. If the latent space looks unstructured or collapsed, it's a sign that the model isn't using it properly and adjustments are needed. Finally, a practical debugging workflow involves starting with a low learning rate and simple model settings. Use small datasets or fewer training steps to quickly identify issues. Track the separate components of the loss to see which part is causing instability. Regularly visualize outputs and latent space embeddings to catch problems early. In the world of generative AI, variational autoencoders are used in image synthesis, text generation, and more. Ensuring stable training is essential for creating reliable, high-quality outputs. By tuning the learning rate, properly parameterizing variance, balancing the loss components, and keeping an eye on the latent space, you can turn a shaky training process into a smooth and productive one. Debugging these issues might take some patience, but the results are worth it for the powerful models you can develop.